All right, we're going to go ahead and get started and hopefully finish up pretty quick. And then you guys will have the rest of the period to do your homework and then tomorrow as well. So I'll open it up. Again, it's the assignment for tomorrow, so you don't have to do anything tonight. But again, it's for tomorrow and you can get ahead. So today we're going to talk about geometric random variables. And remember that geometric random variables are variables that you do your trials until you get a success. So binomial is a fixed number and geometric is not. So in a binomial setting, the number of trials in n is fixed in advance, and the binomial random variable counts the number of successes So the possible values of x are 0, 1, 2. In other situations, the goal is to repeat a chance process until a success occurs. So rolling a pair of dice until you get doubles. In a basketball, attempt a three-point shot until you make one, or keep placing a $1 bet on the number 15 in roulette until you win. These are all examples of a geometric setting. Although the number of trials isn't fixed in advance, the trials are independent. And the probability of success remains constant. Okay, so I'm going to read this lucky day activity for you. I didn't put it in here because it's kind of long, but this is what the activity is. Your teacher is planning to give you 10 problems for homework. As an alternative, you can agree to play the lucky day game. Here's how it works. A student will be selected at random from your class and asked to pick a day of the week, for instance, Thursday. Then your teacher will use technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will have only one homework problem. If the student picks the wrong day, your teacher will select another student from the class at random. The chosen student will pick a day of the week, and your teacher will use technology to choose a lucky day. If this student gets it right, the class will have two homework problems. The game continues until a student correctly guesses the lucky day. Your teacher will assign a number of homework problems that is equal to the total number of guesses made by members of your class. So again, that's just the situation that you're seeing. So in a geometric setting, if we define the random variable y to be the number of trials we get from the first success, then y is called a geometric random variable. The probability distribution of y is a geometric distribution. As with binomial, it is important to be able to distinguish situations in which a geometric distribution does and doesn't apply. So here's that lucky day game, geometric settings, and random variables. The random variable of interest in this game is u, or the number of picks it takes to correctly match the lucky day. Each pick is one trial of the chance process. Knowing the result of one student's pick tells us nothing about the result of any other pick because they're putting the days back in there. So we're replacing. On each trial, the probability of a correct pick is 1 through 7, or 1 out of 7 because there's 1 out of 7 days. This is a geometric setting because y counts the number of trials to get the first success. It is a geometric random variable with parameter p equals 1/7. Okay, we'll be coming back to that. So what is the probability that the first student picks correctly and should say wins? Sorry, y'all, it happens. The lucky day game is the probability that y equals 1 or 1/7. That's also the class's chance of getting only, and that should say 1 homework problem. For the class to have 2 homework problems, the first student selected must pick an incorrect day of the week and the second student must pick correctly. The probability that this happens is the probability that y equals 2. So 1/7 is your success. The first kid failed. The second kid was successful, which gives you a probability of 0.1224. Likewise, if we try to get the third one, so the probability that y equals 3, the first two would have to fail, so 6/7 for both of those, and the third student would get it correct, which gives us 0.1050. So this sets up your general equation. The probability that the first correct pick comes on the kth trial is, so just a general equation. It is 6/7, so your probability of failure, to the k minus 1. So if you look at both of these, if we picked 2, we have 1/6/7, so 2 minus 1, that's where that's at. And then here, if we're picking 3, 3 minus 1 is 2 failures and then a success. So 1 less failure, and then your success. Let's summarize what we've learned about calculating a geometric probability. If y has a geometric distribution with probability p of success on each trial, the possible values of y are 1, 2, 3, ... if k is any one of those values. So here's your formula again for y equals k. For the setting up there, the lucky day setting, we did the failure. Remember to find the failure. It's 1 minus p to the k minus 1 times your 1 success. With our formula in hand, we can now just compute. Sorry, y'all. This is terrible. Any geometric probability. So let the random variable y be defined as in the previous example. Find the probability that the class receives exactly 10 homework problems as a result of playing the lucky day game. And then part B says find the probability that y is less than 10 and interpret this value in context. So for A, we want the probability that y is exactly 10. So remember our formula that you see at the top of the screen? Our success is 1/7, so our failure is 6/7. We want the 10th one, so we have to do 10 minus 1. And then our success was 1/7. So it's actually 6/7 to the 9th times 1/7. And you don't have to show this top work. That's just me showing it for you. You get 0.0357. All right, so what's the difference if I change it to y is less than 10? Y is less than 10. So what does that include if it's y is less than 10? 9 or below. So we have to add all those up, which are probability for 9, 8, 7, 6. So we got to add it all up. So remember, it's 0 problems or 1 problem or 2 problem or 3 problem. So we're going to start with the probability of 1 because they're always going to have 1 homework problem. Add the probability of 2 all the way up to the probability of 9. So the probability of 1 would be that there are no losses or no failures and 1 success. The probability of 2 would be 1 fail, 1 success. We would keep going that same way till we got to 9, which would be 8 failures and 1 success. Now realize you can do this in the calculator, that's fine, but we're just going to show you by hand. When we put this in the calculator, we get 0.7503. Interpret this value. Come on, guys. You're wasting your time. This is the probability that
receiving 9 or less, 10, less than 10
Okay.
homework problems.
So there is about a 75% chance that the class receives less than 10 homework problems. Perfect. Thank you. And then you should finish it like it says it up here as a result of playing the Lucky Day game. I don't care that you do that. Just make sure when you do your AP exam, you're very thorough with that. Okay. All right, everybody good with this page? As you probably guessed, we use the calculator's geometric PDF. And geometric CDF commands for the computations in the previous example. The following shows how we did it. So we didn't do it, but the book did. So things to remember is that PDF is when the probability of Y equals K. So PDF, because it's perfect, we want exactly that. We're using CDF when Y is less than or equal to K. This is the same way as the binomial. It has to be less than. So if you get a greater than, you have to change it, okay? You have to put in the other number. All right, so we're gonna do it. What is the probability that Y is equal to 10? We're gonna do second vars and Geo PDF. Geo PDF. And then what's your probability of success? 1/7. And then what was your X value? We wanted exactly how many? 10. We paste that in there and we get that 0.0356, just like we did before. And you can do 5, 7, or whatever, it doesn't matter. Okay. So if we do the probability that Y is less than 10, we're going to do the same thing, second vars. But we're going to do GeoCDF. 1/7, and then this is not equal to 10. So we want 9 and below. So our X value is actually going to be 9. Second vars, GeoCDF, 1/7, 9. And we get 0.7503-ish. And that's it. Okay, so don't forget that. Again, if you have to do greater than, you're going to change it, that 1 minus or whatever. All right. The table below shows part of the probability distribution of Y. We can't show the entire distribution because the number of trials it takes to get the first success could be a very large number. So if I did this, Y equals 1, this is the value I'd get. If I did 2, this is the value, 3, whatever. But this chart keeps going because we don't have a fixed number like we did in binomial. So that's all it's showing you. Okay. All right. I want to show you this histogram. Sorry. So this is what this histogram looks like. This is geometric probability. Everybody see that? So it starts off large and then it keeps getting smaller and smaller in this case. Okay. So what was the shape of that one? It is right skewed. What does that mean? Large values are less likely. They give you the center mean as 7. We cannot calculate that. Okay. That goes beyond what we're going to do in here. But remember that 1/7 is your average. So from the average 1/7, it would take 7 tries to win. So on average, we would need 7 times. Your standard deviation of y, also something that we're not going to do, is going to be 6.48. If we were doing this one, remember, if it's skewed, we try to find the median and the range. Problem is, what happens with geometric is it continues to go, so we can't even find that. So that's why they use the mean and the standard deviation on this. But again, we're not ever going to be asked that because we're not going to find that in our course. Okay, it's beyond what we do. We can generate the result for the mean, should say, of a geometric variable. The mean or the expected value of a geometric random variable. If y is a geometric random variable with the probability of success p on each trial, then it's a mean or expected value. So your mean, or you can see it as expected value, is 1/p. That is, the expected number of trials required to get the first success is 1/p. Now hang out here for just a second and I'll show you what it means. Our p on the last one was 1/7. Remember, we don't divide fractions. We flip and multiply, which gives us 7. Okay. All right, any questions on that page? Last one. All right, almost done. Suppose you roll a pair of fair 6-sided dice until you get doubles. Let t equal the number of rolls it takes. Show that t is a geometric random variable. Why is something a geometric random variable?
It doesn't have a fixed number of tries.
So we're going to roll until successful, regardless of how long or how quick that is. Good. How would we figure out, a binomial? What if it fails independence? Check the
Large counts.
Nope, not large counts, 10%. What's large counts do? Remember, I told you everybody mixes that up, so don't feel bad about that answer. Everybody mixes it up. What does large counts do? Ooh. It changes from binomial to what? To normal. So we want to make sure that we can do the large counts and see if we can use normal instead. So that way we don't have to do any of that 1 minus or anything, any kind of crap like that. Okay. All right, number 2. Find the probability that t equals 3. All right, so first of all, I need to know what my p is, not this p, but my little p. What is my probability of success for rolling dice? 1 out of 6. Okay. Very good. All right, so we said that this was geometric because we keep going. So we can do this 2 ways. I'm going to show you by hand because this one's little, and then I'll show you by calculator. So probability t equals 3 would be the failures and the number of failures. So failure percentage would be 5/6, and there will be 2 of those because we'll roll twice, and then we'll succeed on the 3rd roll, which gives you 0.1157. How would I put this in my calculator? Which one would I use? PDF because it's equal and that's perfect. What's your P? 1/6. What's your X value? 3. And that'll give you the same thing. Okay. I don't care which one you use, but make sure when you do this, you write this out. Interpret this result. Don't for gosh, please stop missing that word. Please interpret. What's it mean? That? Sorry. You will get doubles on what? Your first time on 3 tries or 3 rolls. Perfect. In the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability that this happens. So the difference in this question is this right here, within 3 turns. So what does that mean?
Less than or equal to.
Yes. So they could do it within 1 turn, 2 turn, or 3 turns, just as long as it's less than or equal to 3. To do that by hand, remember we would have to do the probability of 1, the probability of 2, and the probability of 3. 1 would be no failures and 1 success. 2 would be 1 failure, 1 success. And 3 would be 2 failures and 1 success. Or we can put it in our calculator how? CDF. What's our P value? Sorry, I was doing the last problem. 1/6. And what is our X value? 3. Why is it 3 this time? Because it's equal to 3. Very good. Both of those are going to give you a 0.4213. So there's a 42% chance that this will happen, that you will get out of jail free within 3 turns. All right, that's all I have. Like I said, I'm going to go ahead and jump in there. I'm going to stop sharing and open that quiz.